I just wanted to ask you.
So, today we're going to speak about SN1 and SN2. Primarily, we will not be doing anything extra for OMA level, but some teachers might not have done or covered all the material. So let's make sure that you are up to standard with what we require here. So SN1, you have a nucleophile. The nucleophile will attack, sorry, that's SN2. SN1, you have your halogen breaking to form an ion and the carbocation. The carbocation is going to be planar. Can anyone tell me why the carbocation is planar? Increased stability. Others? It only has 3 bonds and no lone pairs. So the furthest away for the electrons to be would be at an angle of 120 degrees. It will result in increased stability, but increased stability on its own, it's not enough. And we'll speak a little bit about the CH3 stabilizing groups. And then we will add the nucleophile. And that will give our final product. Okay, and this is the SN1 mechanism. Again, I'm going to go relatively quickly through these. If you have any questions, I'll leave you some time to ask at the end of the lesson. For SN2, you will have a halogenoalkane as well. I'm gonna use the same halogenol or the same bromo compound, but this time I'm using a primary. And we'll speak why primary is important here soon. The nucleophile will attack the carbocation, which is slightly delta positive, and this will release the electrons to the bromine to give an interstitial or a transition step, okay, where you will have bonds being broken and bonds being created. And the charge here will be negative to then give the final product where the nucleophile will add at the end. We'll speak. So someone asked me, what about secondary halogenoalkanes? We'll speak. We haven't really spoken yet what happens with SN1 and with SN2. Okay? We haven't really spoken about those yet. We'll speak about that in a minute. And then we'll know that for secondary, there are going to be a few principles which we will be speaking about later on, both today and in a few months' time when we do what we call elimination reactions. Okay, I don't know if anyone set for foreign exams, but halogenoalkanes do not just do substitutions, you can also eliminate the halogen and the proton to make alkanes, for example. Now, these are the energy diagrams, and you can see that for SN1, you have 2 peaks, but what's important is the intermediate. You have an intermediate. Intermediates can be trapped. Intermediates can be trapped. It's hard to trap them normally, but intermediates can be trapped. You require only a little bit of energy to get them to move forward to your final product, but intermediates can be trapped. On the other hand, for SN2, there is only one step, okay? Therefore, you have no intermediate products. This is only a transition state. The transition state is the highest state, okay? The transition state is the highest state in the energy diagram, and this will then react to form your product. And there is no possibility of stopping it. Intermediates. Now, intermediates for carbocations are highly unlikely to be stabilized. One of the few ones that I know that is stable is this carbocation. That's supposed to be a benzene ring. Sorry, I really can't draw. This carbocation is stable because there are 3 phenyl groups stabilizing it. Okay? In fact, that proton is highly acidic. But most carbocations that we see in SN1 reactions, you would not be able to stop them. Now, here we have a tertiary carbocation. Who can tell me why this is more stable than a primary carbocation?
3 plus I effects. 3 plus I effects.
3 inductive effects, okay? Is everyone in accordance that we have 3 methyl groups that are affecting, 3 methyl groups that are affecting that carbocation? Is there anyone who does not believe this is the inductive effect? Chet, you are active normally. What happened today? New Year blues? This is not the inductive effect. I know that at A level, okay, you were told it is the inductive effect, but it is not the inductive effect. In fact, it's called hyperconjugation. And we're going to spend the last 20 minutes before we have any questions speaking about hyperconjugation. Okay? Now, first things first. It makes sense to include it as an inductive effect at A level because it is simpler. Okay? And at A level, we don't want to introduce too many terms. But let's draw let's draw it like this. What is the hybridization of a carbocation? Who can answer? sp3, okay. Anyone? So I had sp3 in class. And what do you think?
Me?
What is the hybridization of any carbocation?
I'd say sp3 as well, I'm not sure.
There is a free orbital there, right? So it's sp2. So carbocations are always sp2 hybridized. In fact, this is why they have an angle of 120 degrees, why they are planar, because sp2 carbocations, they only have 6 electrons. So they have 6 electrons, and you have 4 orbitals. One of the orbitals will be empty. If one of the orbitals is empty, then you will have sp2 hybridization. This is similar to what you have in carbonates, even though you have full access of electrons there, you still have sp2 hybridization because it increases stability. Okay, it puts the electrons as far away from each other as possible. So what happens here? Each hydrogen is in a s orbital. Do we agree? And these are constantly rotating. So what happens is that the electrons in the hydrogen can interact with that empty p orbital. So electrons in the s orbital can interact with the empty p orbital. So what do we get? We end up in a situation where the more CH3s we have, the bigger the number of s orbitals that we will get. Okay? The more CH3s we have, the number of s orbitals that can interact with the p orbitals. Okay? Now, in fact, there is not a big difference between having a CH2 or a CH3. That's why we say the alkyl chain does not matter. It doesn't matter that much. There is a slight difference, but not a big one. There would be a difference, for example, if you have something like this. Okay? And as far as I'm concerned, even here, there will still be some overlap because of the rotations and angles in space, but it won't be as much. Okay? So that carbocation will still be stabilized a little bit. Now, so this is hyperconjugation. It's the interaction of the electrons in the s orbital that can interact with electrons in the empty p orbital. So, having spoken about this and having actually seen that there is a bit of a misunderstanding maybe on the electrons and where they are in orbitals in carbocations, what I will recommend is that for question 3, also write the hybridization of each of those atoms. Okay? The hybridization of each of those atoms. Remember, there should not be a change in hybridization when you have resonance forms. As far as I'm concerned, it's never the case. Okay? Now, I might be wrong about that, but as far as I'm concerned, I think it's never the case. Okay? At least in the major ones, it wouldn't be. There might be some minor forms where you manage to do it. Okay? So that would be something that you should note. Now, let's go back to SN1 and SN2. Because of this hyperconjugation, the stability of the carbocation, okay, tertiary carbocations are much more stable than primary. And therefore, tertiary carbocations will normally undergo SN1. On the other hand, SN2, we normally have a situation where primary carbocations offer less steric hindrance then tertiary. Therefore, allow for more reaction. Now, steric hindrance. For those of you who might not know what this is, okay, or for those of you who might not be too comfortable with it, okay, steric hindrance is the effect of adjacent groups on each other. Okay? Pretty much, we also call it repulsion. Okay? So let's assume I go out to Portugal, all the students I've seen come and speak to me, and you don't let me speak to any girl my age. Okay? You are steric hindering me from meeting someone else. Please, if you see me at PV, consider the time at what time you see me. If you see me before 11, come and speak to me, it's fine. After 2, avoid it. I might be drunk. I'm still your lecturer. Okay? But I haven't gone to PV in the last 6-7 months because of COVID, so for now, you're safe. Plus, please also consider, for the ones that are at home, you might see my face, I don't see yours, so I will not recognize you. There was a student last year who I had been teaching for 4 or 5 months in class, every single week. I saw her outside, I was completely sober, and I had no idea who she was. In fact, I thought she was a student from the course I was in 10 years ago. She was not offended, but I was surprised.
So
Okay,
unless I speak, you won't know who I am, for example.
If you speak to me outside of the classroom, I won't know. But here, I gotten used to your voice over a computer screen. So I might
That's
still
good to know.
recognize you. And I have, at home, I printed a dartboard with your face on it now.
Don't blame you.
Don't worry, don't worry. I don't mind your questions. Plus, after all, you are representing the whole course. So you can be as mean as you want, and you can blame it on the others. Back in my day, I used to do that. So, now, why are we speaking about SN1 and SN2? So, in reality, there are other factors in play here. But if you don't know these, you will have a very hard time in the second semester, because we're going to speak about solvents, and we're going to speak about nucleophiles. Okay, so nucleophiles, and also about leaving groups. Let's mention them here as well. So the nucleophile, this triggered the nucleophile, the more it wants to react. But nucleophile's size matters. Okay, so if you have a small nucleophile, it's going to play a role because it can go in and attack. If you have a big nucleophile, something like this, okay? If you have a strong nucleophile and a big nucleophile, then that will not be able to attack your halogenoalkane. And this is a nucleophile you might have never seen before. Anyone knows what the group is? It's not an alcohol. Alcohol would be with an OH. It's an O minus. So what would it be?
Alkoxide.
The alkoxide. Okay? And alkoxides are very, very strong bases. In fact, if we were to see the equilibrium Okay? If we were to look at the equilibrium shifts, is shifted highly to the left. In these reactions, can you use water? Can you use water in these reactions?
No.
It's not about non-polar. You can't have any acidic hydrogens. Okay? So normally we use ethers. So these would be dissolved in ether. Okay? Ethers are not apolar. They are just not acidic. Okay, we use a ethyl ether. So anytime you have a strong acid, make sure, a strong base, make sure that you do not use water. In an exam, that would be a big, and that gives you nothing. Because I would think that you have not understood anything. Okay? Now, that's with regards to the nucleophile. The solvent. Some solvents make nucleophiles stronger. For example, if I have H plus in water and H plus in ether, they behave differently. Okay? If I have H plus in water and H plus in ether, they will behave differently. Because one is polar and protic. We'll define what the term protic is later on, okay? But it normally has to do with being able to form hydrogen bonds, and the other one is not. So in water, it will hydrogen bond and interact with the water atoms. In H plus, in ether, it doesn't. So in one, it's called an acid. And the other one, it's an electrophile only. And in fact, H plus in water would have a pH, H plus in ether would not. Now, someone pointed out, I think it was before the Christmas holidays, there can be pKa's of organic solvents. Yes, you will have a pKa value, but if you realize most of those pKa values would be pKa and 20, for example, it's a huge number, which would mean that the amount of H plus is minimal. So it would be 1 times 10 to the minus 20 if it is pKa 20. Even alkanes, okay, would have some hydrogen atoms, ions released in solution, but they would be minimal, okay? There is always something. And the leaving group, having bromine, iodine, or chlorine is different. If I have this, the reaction will be very fast, but if I have the chloro, the reaction will be so much slower. Okay, so why? Anyone tell me why the iodo-carbon bond would be a fast reaction, but the chlorocarbon bond would not? So iodo-carbon bond is a longer bond, okay? Therefore, it's weaker and easier to break. Apart from this, okay, electronegativity of iodine is greater, smaller. Therefore, it will be pulling on the electrons less, easier to break. Now, of course, when we speak about these effects, these three effects, okay? 1, 2, and 3. It's not going to just be with respect to substitution reactions. We're also going to be speaking about elimination reactions. And up to now, you have done CH3, CH2PR, OH minus in alcohol to give CH2 double bond CH2 plus HBr. Okay, and we can see that the solvent here was water, whereas when we used the reaction in alcohol, sorry, that's the aqueous, just make typo. Sorry, I said water and I wrote aqueous, alcohol. Whereas the other one, in alcohol, you will get substitution.
Ser,
No, I'm wrong. I was.
aqueous OH mhux toħloqlok l-alkohol, imbagħad alcoholic KOH joħloqlok
Yes,
l-alkeen ser.
yes, yes. 1 second. I confused myself. These should be my bread and butter. NaOH, aqueous, then alcohol. Sorry, my bad. Now, and this is because when you have the OH in water, it behaves as a strong nucleophile, okay? So it can attack, whereas when you have it in the alcohol, it will behave as a base, similar to the H+, okay? And we'll be speaking about these in a lot more detail, okay? Because then we're gonna have, similar to SN1, we'll have E1, elimination 1. And similar to SN2, we'll have E2. Now, for these reactions, there will be a set of rules. If you learn the rules, then you will be fine, okay? But of course, you would need to learn the rules. And back in my day, so I'm speaking around 10 years ago now, okay? It was the case where students who did not bother to learn the rules would get a C, a D, or an F. And students who learned these rules would get an A, a B, or a C. There was still a range, but if you don't get these questions correct, you can't get the high marks, okay? And you'll see from papers, and I will be giving you quite a few papers. So for second semester, expect to work on this subject. Now, so for today, with regards to material, new material, that's all I want to speak about. 1 second. So, Kristen, for your first question, we won't be answering it today, but if you have a secondary halogenoalkane, okay? If you have a secondary halogenoalkane, then you will not get one or the other, you will get both. In fact, you will get 4 products, not 2. You will also have the elimination. So secondary, you can't really say if you're gonna do one or the other. We will be discussing those in further detail in the second semester, but normally you get a mixture of products, a mixture of mechanisms, but it's the same product. For the orbitals, okay, what happens is this. This carbon is rotating, right? When that carbon is rotating, it's gonna get the hydrogens to us close to the empty p orbital. Therefore, there will be some interaction. Remember, these are 3D. So since these are 3D, there will be rotation over that bond. And once there is rotation over that bond, there's going to be an interaction, then it stops. Then there's an interaction, then it stops. It's similar, I dare say, but to a hydrogen bond. It's there, then it's not. It's there, then it's not. And every time there's an interaction, it will affect the carbocation, the positive charge. In fact, it will reduce it. It's not a bond. Hyperconjugation doesn't produce bonds. It is just an interaction. So it will just minimize, okay? It will just minimize that carbocation, that positive charge. So